Hello class, welcome to the channel and welcome to this playlist in which we are discussing about different type of transformations which provide us transform from time domain to frequency domain. So up until now we have seen Fourier series, Fourier transform and Laplace transform. We have also seen the inverse of Fourier, which means Fourier inverse or inverse Fourier transform. We have also seen inverse Laplace transform. So today we are going to discuss about the discrete time Fourier transform. So basically it is a Fourier transform. So there will be not so much change in the formula, but the signal which is going to be converted into the frequency domain from time domain will be this time the discrete time signal. Up until now we were seeing for continuous time signal. So this time we are going to see for discrete time signal. Okay. So this discrete time Fourier signal, or in short DTFT, is used for the analysis of non-periodical discrete time signals. So come to this slide. Let's talk about the definition of my DTFT. So let's say we are taking a discrete time signal x of n, which you can see here in this formula, and if I have to find the discrete time Fourier transform of my x of n, then it will look something like this. X of omega, which is the discrete time Fourier transform of my original signal, will be equal to summation n is equals to minus infinity to infinity x of n into e raised to minus j omega n. So that is your discrete time Fourier transform equation, and it is also called analysis equation. Omega is the frequency of my discrete time signal, and the range of this frequency will be minus pi to pi, right? So if you sum it up, it is equivalent to still it is equivalent to 2 pi, which means you are going around the whole circle, and during this whole circle the radius will be same, so pi will be the continuous in this range. And if you want to define your x of omega, then you can call it spectrum of your discrete time signal. So even if my x of n is discrete, its spectrum will always be continuous, which means x of n can have all the frequency from minus pi to pi. Also, if my DTFT of my periodic signal, if I want to calculate it, I can calculate that as well. And the spectrum of this signal, the periodic signal, will be discrete this time. And why is that? It is because periodic signals will always have the discrete spectrum. Same ways you can also find the discrete time Fourier transform of basically you can find the inverse DTFT, inverse discrete time Fourier transform. So in that, what you will do this time, initially you are going from time domain to frequency domain. Now you will be going frequency domain to time domain. So this time the equation I want, like the output I want, will be in the time domain. So it will be my x of n, and I can give the formula for x of n is equals to 1 by 2 pi minus pi to pi integration x of omega e raised to j omega n into d omega. So the integration is being used here, and since x of omega is the continuous function of omega, then the range will be from minus pi to pi, and because of that we took the limit of this integration minus pi to pi. And you can obviously say, if my range is minus pi to pi, then what will be the what will be the period of this range. So the period will be pi minus pi, which means pi plus pi is equals to 2 pi. So the range will be 2 pi. Sorry, the period of the integration will be 2 pi. So this way you can find the DTFT of any signal. But in the definition of my discrete time Fourier transform, we have seen this the summation over infinity range of n is taken, which means my DTFT exists if the convergence of this summation is possible. But you can only find the DTFT of your signal if your original signal, which was x of n in this case, is holding values less than 0, or is a finite signal, right? So if x of n is not absolutely summable, then it should have finite energy for DTFT to exist. So that is the condition for the discrete time Fourier transform of my signal to exist. So it is again very similar to the condition which we when we saw same thing about Laplace and Fourier as well. So that thing will remain same. And now to discuss about the properties of my discrete time Fourier transform. So again, the discrete time Fourier transform will also hold the same same properties which were holded by my regular Fourier transform. So you can see here periodicity, one new added property here. And what does it tell us? That my x of omega is is periodic with period 2 pi, right? If x of omega plus 2 pi k will be equal to x of omega, right? So basically if you add 2 pi to your 2 pi k to your original signal, the Laplace of your original signal, you will get the Laplace itself back. Sorry, not Laplace, Fourier itself back. So that's periodicity for you. Then again we have linearity, and linearity will be very same. So we have discussed it in detail, so I'm not going to prove it one more time to you. So if you want to check out the properties of Fourier transform, please check out the link which will be flashing on the top right hand side corner on the screen in the I button, so you can check it out. Now again the linearity property, it works on superposition theorem, we all know that. And we know how the linearity property works, right? If I'm having a signal which is which is called Zn, and if Zn is the summation of ax of n plus by of n, then whenever I find, or whenever I derive the value of z omega, which means the discrete Fourier transform, discrete time Fourier transform of my Zn, then this z omega will also be equal to x of omega into a and y of omega into b. So they are remaining intact, okay, there is no change in them. So that is your linearity property. Now we can also use the time shifting property here. So if I delay my signal by some n0 number of samples, then my discrete time Fourier transform will get affected as well. So let's say if I'm having a signal y of n is equals to x n minus n by 0. So whenever I take the discrete time Fourier transform of this signal, then what I will get y omega, which is equals to e raised to minus j omega n0 x of omega. So that is a time shifting property, we have already seen it, so I'm not going into detail of that. Then we have the frequency shift as well, and it tells us almost similar story. So whenever you make change in your frequency, there will be change whenever you make the change in the frequency in your Fourier domain, there will be change in the time domain as well, right? So what does it states? It states like y of n is equals to e raised to j omega 0 n x of n, and its discrete time Fourier transform will look like y of omega is equals to x of omega minus omega 0. So that's your frequency shift. Then we have the scaling property. The scaling property I'm not going to explain because it basically remains very identical, very similar to the one we discussed earlier. Then we have the differentiation in frequency. So this one is also we have discussed a little. So whenever you take your complex number in time domain and take the discrete time Fourier transform of your that signal, what will happen? The you will get x of omega, but you will get d by d omega x of omega. So whatever your Fourier transform is, DTFT is, you have to differentiate it in the frequency domain, and that's what the differentiation in frequency domain tells us. Then we have the time reversal. Again, it is a very same concept which we saw earlier. We saw that if my signal is y of n, and if y of n is equals to x of minus n, then the DTFT of my y of n, which is y of omega, and DTFT of my y of x of n, x of minus n is x of minus omega, then y of omega will be equal to x of minus omega, right? Pretty simple. It's time reversal. Then we have the convolution property. It says if I'm having two signals who converge in time domain and give us some output Zn, then whenever take the discrete time Fourier transform of those two signals, their multiplication will give me the multiplication of their Fourier transforms will give me the Fourier transform of my final signal, right? So that's the convolution for you. Then we have the multiplication. So the multiplication, but multiplication in time domain. So earlier we called it modulation, so we still call it modulation. In this, same thing will happen whenever you take two signals and you multiply them together and you name it one signal, and then when you take the discrete time Fourier transform of your signal, you will get convolution of your original two time signals. So you will get convolution of not the original two time signals, but the DTFT transforms of original two times time signals, and the whole thing will get divided by 2 pi, which is basically the whole area. So that is the modulation property for you. And then the last but not least, we have Parcels Theorem. And again, we have studied theorem in detail, so I'm not going to explain everything. So the basic thing is what Parcels has suggested is whenever you take your any discrete time signal and whenever you do the DTFT of it, you will get x of omega, which is the Fourier of it. Now, if the energy of the signal is given to E is equals to 1 by 2 pi minus pi to pi x of omega whole square into d omega, then what will happen? We are already aware of the energy we are having. So E will be equal to summation n is equals to minus infinity to infinity x of n whole square, and this x of n whole square is also required to maintain the it is also required to take the multiplication of x of n and x of conjugate of x of n, right? So basically the Parcels theorem gives you the formula of energy of your signal based on the frequency transform of your signal, and that's pretty much sums up the properties of discrete time Fourier transform. I'm not going into very much better details of these properties because we are running out of time here. So I hope you understand. Uh, Even though if you prefer the book and try to find out the doubts in this, you can feel free to contact me anytime. I will be available here. So we are cutting it short, and now we are moving forward to the frequency response of my discrete time signal. So let's say I'm having a signal, and basically I'm having two signals. So I'm having uh, my output as y of n, which will be equal to summation of k is equals to minus infinity to infinity h of k into x of n minus k. Now what will happen? We will take this x of n is equals to e raised to j omega n, and when we do that, what we will get? We will get y of n is equals to summation k is equals to minus infinity to infinity h of k, which remain as it is, e raised to j omega n minus k because the minus was also present there, minus k was also present there, right? Then what you will do, you will take the e raised to j omega m outside the summation mark. Then you will take summation of k is equals to minus infinity to infinity h of k into e raised to minus j omega k. So that was that was the frequency response of my discrete time signals. Here what will happen, my e raised to j omega n will be my input signal, and h into e raised to j omega are the frequency responses. So the DTFT of my h of n can be given can give the frequency response of the system as well. Now from DTFT, let's quickly move towards the DFT or Discrete Fourier Transform. So now that we know that the DTFT is giving us the Fourier transform of my discrete time signal x of n, which is basically x of omega. So the DTFT is continuous in omega, right? It is continuous in omega from minus pi to pi, and because of that, DTFT cannot be calculated on digital processors. Why? Because digital processors want samples. You cannot go with continuous signals, and because of it, we need to calculate the DTFT at discrete values of omega. And I know you might not like it because I always say that we try to find the discrete we try to find things in discrete because we want to work on processors, but here only in this case it will not be very much beneficial if we go for DTFT in case of processors. So there is another different type of transformation available for processors only, which is which is the transformation which we are going to study next. So whenever we try to calculate DTFT at discrete values of my omega, we know that the total range of omega is moving from minus pi to pi, and basically if you sum it up, it is 2 pi. So if omega is sampled at n points, then there will be 2 pi by n points, right? Wait a minute, I didn't change the slide, you didn't remind me. No issue, come here. So again, if I'm taking n number of samples, then there will be 2 pi by n points, right? And because of that, you can write the equation of your DTFT as this equation, right? X of 2 pi by n into k is equals to summation of n equals to minus infinity to infinity x of n is to minus j 2 pi divided by n k into n, where k's value will keep varying, right? And this thing is called aliasing. If you are a person of image processing, if you have studied image processing a little, you might know that you might know this term, because in image processing domain it is kind of a nuisance to us because we don't uh, use aliasing. It's very frustrating when you get aliasing in your picture, so you try to remove it. So it is bad in the signals as well. And to avoid this aliasing effect, because of the sampling the frequency spectrum, what do? The number of samples n must be least equal to the length of the sequence x of n. That's the best way to avoid my aliasing effect. In other words, I can say if my x of n has n values, then uh, DFT or sample DTFT should be given as this formula only. X of k is equals to summation n is equals to 0 to n minus 1 x of n e raised to minus j 2 pi f 2 pi kn divided by n. And this term x of 2 pi by n into k, you can, instead of this whole term, you can write k, right? So the k is the index of frequency in the frequency domain, and inverse DFT or IDFT can be obtained from DFT as well using this formula as given. This is the inverse DFT formula. Same way as we found the inverse of Laplace and Fourier, we can find the inverse of DFT as well. So it is given as x of n is equals to 1 by n, summation of k is equals to 0 to n minus 1 x of k e raised to uh, 2 pi k into j divided by n. There's the formula. In this, the value of n will keep changing. Now let's see my discrete Fourier transform as a linear transformation. Doesn't make very much sense, but let's see what it has to offer. So what we will do initially, we will define it using Wn, which is equals to e raised to minus 2 pi j divided by n. And by the way, this thing is also called the twiddle factor. So instead of writing it in a very long format, you can use it twiddle factor, right? So x of k will be equals to summation n equals to 0 to n minus 1 x of n w n to kn, and here the value of k will keep fluctuating from 0 to n minus 1. And for x of n, it will be, because initially we saw the Fourier transform, right, discrete Fourier transform. Now we want the time domain back. Basically we want time domain signal back. So what we will do here, so we will take DFT and IDFT equations, and what we will do, we will simply put the values of Wn is equals to e raised to j 2 pi divided by n. So when we replace this sequence x of n as my vector xn of n number of samples, the formula I will get will look something like this. We will have x of n, the n equals to 0, n equals to 1, all those values will fall behind or fall out of the side, but the other values x0, x1 up to xn minus 1 will remain there. Now you can write the same ways for x of k as well, right? In the same ways x of n represented of n samples. So x of n will equal to, here in this case, the value of k will remain outside, k is equals to 0, k is equals to 1 up to k is equals to n minus 1, and x of 0, x of 1 up to x of n minus 1. And this only value of Wn, you can represent it using the matrix form as well, right? And now you know how tedious work is it and why processors are used for all this work, right? So the formula will look something like this. You can see the matrix. It's pretty much very big matrix because we are calculating for n equals to 0, then 1, then 2, then 3, and I'm not sure how far does it goes actually. So basically the final formula of my Wn will look something like this. You will have Wn0, Wn0, Wn0 up to Wn0 for the first row. Then we have W0, Wn1, Wn2 up to Wn n minus 1. So here you can see the individual elements are written as W of n by with k rows and n number of columns, and then we are having n points of DFT of equation, this equation, the long equation, and you can represent it uh, in the matrix form as well. So you can give x of n is equals to omega n or wn into small x of n, and same ways you can find the IDFT as well. So the formula for IDFT has also been given here. Now let's move forward and discuss about the periodicity of my periodicity of Wn. So in the calculation of Wn, what we will take care of certain things. Initially we will check the value of Wn if it is n is equals to n8, and we know that Wn is provided us with this formula. Wn is equals to e raised to minus j 2 pi divided by n, and same ways with n's value 8 you can obtain W8, so it will be e raised to minus j pi by 4, right? Because 2 pi by 8, so basically you will get 2 pi minus j 2 pi by minus j pi by 4. And same ways if you want to find further, you can do that as well. Now to plot these values, so when you substitute values of 1 2 3 4 5 up to uh, probably a 13, so what you will get a graph like that. Here we have calculated value of W8, which was, what was the value? The value was e raised to minus j pi by 4. Now you already know what is the angle pi by 4. It is 45 degrees. So if it is a 45 degree, yeah, it is. It's equals to 1 by root 2 minus j 1 by root 2 into 1 by root 2. And you can also see the rest of the values have been plotted here as well. After that we will move towards the Z transform, but I think that today's class has been stretched a little bit far, so let's keep this class till here. We will discuss about the Z transform in the very next class. So if you have any doubts, any queries, any questions, or any feedbacks or suggestions related to the channel or related to videos, please feel free to mention them in the comment section below. I will try to answer all of them as soon as possible and as quick as possible. Also, please give me the feedback about this playlist in particular, if you're liking it or not, so that I can know that if you guys are expecting such kind of content or not. So we will keep this lecture till here. Thank you very much for listening, and I will be seeing you next time. Goodbye from now, and one more time, thank you very much for listening.